Hello, I hope you enjoyed this conference. I will talk about YugabyteDB. Basically, it looks like Postgres from an application point of view. And it looks like Postgres for the application developers because it is a fork of Postgres you connect to. And also from a cost perspective, because it is fully open source. It's different in the deployment because it's cloud native and it can scale horizontally. So basically, you can run your Postgres application in a cloud native environment that brings elasticity and high availability. Let's look about that. Few words about myself. I've always been working with databases, a lot of Oracle, some Postgres, some AWS databases. You see a few logos. Those are the certifications I have. I even passed a MongoDB certification, but I'm really a fan of SQL databases. You have my LinkedIn, my Twitter, and I'm publish a lot of articles online. So if you want to follow, just follow LinkedIn and Twitter or X, as we should say today. Postgres. You can run many things on Postgres. It's one of the most popular open source database today. And people tend to say that you can use Postgres for everything. Um, it's popular, it's open source. It works well. You can run with high throughput if it's well tuned, probably not the default configuration, but you can run it if you have the DBA and Postgres expert with high level of transaction throughput. And you can also provide good availability. I'm not saying high availability, but good availability. Because you can have a standby database and you can automate the failover with Patroni, for example, or when you run on managed services. Let's talk about managed services. When you look at it, you can run a lot in Postgres, but when you look at it, a lot of companies are not directly running on the community Postgres. They are using managed services and adding some extensions. And the question will be, what is missing in Postgres that has to be added with extensions or forks in managed services? And basically, a lot of them are about replication because Postgres is monolithic, a single server. You want to protect it with some replication or distribute it with some replication. A lot of different solutions bidirectional where you have multi-master, but then you have conflicts if you write on both sides. Sharding, where you split your workload, you have a sharding key that the application must know, and you split your workload to multiple databases. Examples, Citus in Azure or Limitless. There are also some solutions that still use a fork of the monolithic Postgres, but they have distributed the storage behind it, like Aurora, LoyDB, Neon, distributed to a cloud native storage, but still a single instance. And finally, those distributed SQL solutions, and Yugabyte is one of them, where you truly run distributed. The application can connect to any nodes, see a global database with all SQL features and all ACID properties, but in behind it is running on multiple servers and can be resilient if some servers are down. So we will look at about it, but first the question is, if you can do everything with Postgres, except that it is monolithic and you need forks extensions to break this monolith, why do you need to break this monolith? And there are multiple reasons today. A lot of companies want to run on public clouds just because it's easier than building a data center and running a data center on premises just for your company. And when you go to the cloud, you want more high availability and you are concerned about latency and the big advantage in public clouds is that you can easily run on multiple data centers. On premises, you will not build 3 or more data centers that are close enough for low latency, far enough not to burn at the same time. In the cloud, it's really easy. When you provision a new virtual machine, you just choose a different data center. So you want to use that. But in public cloud, resources can be expensive if you use them like you do on premises, like provisioning, starting the VM and let it run at its full shape for your workloads to absorb the peak of workload, or being idle if it's out of the peak. If you do that in the cloud, it will cost a lot. In the cloud, you want more elasticity. You want to be able to scale up or scale out when the workload increases, but also reduce. And you want to do that without downtime. The point is that you can deploy on multiple data centers, but you don't want to deploy the full power on multiple data centers for the whole year, for example. So another thing also, when you are in public cloud and you use managed service, means that it's not the DBAs are not your employees. They are the cloud vendor employees. And it makes things a bit more difficult if what they have to do, the operations, needs some downtime. When you are on premises, it's quite easy. The DBA can call the users like, I need to patch the database. Can I restart it on Friday during lunchtime? And that's possible. You cannot do that with a cloud vendor. AWS will not call you and asking you, when do you go to lunch? You have to define in advance maintenance windows. So going to the cloud, there is this need to operate without downtime at all. So being able to scale the database without stopping the application, but also being able to upgrade the database without stopping the application. And of course, in a public cloud, it saves cost because it runs on commodity hardware, but failures are much more common than on premises. So it must also be resilient to failure, not stopping the application just because a network switch is down for a few minutes. But that works also on premises with private cloud, for example. You want to virtualize, you want to run on Kubernetes, and then you want a database that can scale horizontally. On Kubernetes, you can scale a stateful set with multiple pods. But if you run a monolithic database where only one pod is active, you don't really benefit of the scaling. You really want a database that scale with the pods. In the demo I will run the demo on Kubernetes, on AWS managed Kubernetes, Amazon EKS, and we will see that. But first, we understand why we want to break this monolith. But what is monolithic in Postgres? What do we have to break to do that? Think about the application. The application connects to the database to a single node. You have only one primary instance in Postgres that can take your consistent reads and writes. And then the backend in this node will read and write not directly to the storage. It reads and writes to and from the shared buffer, the shared memory between the processes. And this also is monolithic because you are in a single node. You cannot share the memory with multiple servers on the network. And the writes happening in memory must be protected, written to disks. This is the write-ahead logging, or what is called redo log or transactional logs in other databases. And this, again, is monolithic in the sense that it is a single stream of changes. If when writing the write-ahead logging, for example, to disk, if it's slow, it will block all changes for the whole database. It's a single wall stream. And everything below that can scale. The storage is not monolithic. You can run on multiple file systems, and those file systems can be distributed on multiple disks, multiple in network storage, block storage in the cloud. Storage is not a bottleneck, but you don't really depend on that because it's written to storage by checkpoint asynchronously. The things that you are waiting for, writing to the shared buffer, connecting to a single node, those things are monolithic and you pay the price with the application then. Because the problem is that when it is monolithic, if this primary instance is stopped, if it crashes, then you don't have the memory anymore and you have application downtime. So to summarize, what is monolithic? Connections handled by a single process for your session on a single server, a single shared memory holding the shared buffers, and protected by the write-ahead logging. That is, again, one execution stream. Now about scalability and divability. The problem being monolithic is that if there is any failure in those monolithic components, then all current sessions, current transactions are stopped, receive an error, the transaction will be rollbacked. They will have to reconnect and restart what they were doing from the beginning of the transaction, and also know exactly where to restart. This failover takes time, even if you are protected with a standby that can be up quickly in a few minutes, like for example in AWS Aurora. It still takes time because if the primary is not available, basically you don't know if the primary is not available, if it's a network issue. The standby that starts and is activated as the new primary must be sure that the old primary is not available. And it starts with a cold cache, and the application has to reconnect to it. So you have a connection storm to it. Many reasons why, even if the failover itself takes a few minutes, it takes a bit more from the point of view of the application to get full availability again for the database service. And it's a full downtime. All connections to the database are down and have to fail over. And even if there is no failure, I mentioned that you don't want to provision immediately for the highest peak of workload. You want to be able to scale and scale up because it's a single server. And that's also a problem because it's easy to scale up. You stop the database instance and start with a larger instance with more vCPU and more memory. But I said, you stop it, you start it, and because it is monolithic, all your connections are connected to it, and then it's like a failover. They will have to reconnect. They will start with a cold cache. So scaling up is still a downtime. And scaling out is just not possible because of those monolithic components. The only thing that you can do with Postgres itself is adding more read replicas that can serve stale reads. They are not aware of the current state of the database, but for reporting, it may be okay to query as of the past minutes, for example. But that's limited to the read-only scenario. And you also have to identify that from the application to connect to a specific endpoint for those read-only things. One more thing about scaling up, think about when you really have to do that. And this is an example of what happens for Black Friday for a lot of applications. You want to scale up for this week where you know that you will have a very high workload. But if you have to stop and restart to scale up, when do you do that? You will not do that just a week before, because the load is already up and you don't want to stop application at that time. So finally, you will scale up long time before, many months before, and you don't need it. So it's not very cost efficient. So in short, scaling up is downtime. Scaling out, you want to scale out and then look at the solutions for that. And the solutions are replication and sharding. To scale horizontally, we must split the database at some point, run some part of the database in different servers, and then, of course, replicate them. And there are two ways to shard that. One, the first you may think about if you run with the standard Postgres, is sharding on top of multiple databases. So the application knows that this set of customers are stored in this database, this other set of customers are stored in the other one. How to define the sets? Maybe you look at the customer number and even odd ones or by their country, but the application must do that. It's more code in the application that is not directly business logic, but data logic. Can be easier with a coordinator, and that's what the Citus extension is doing, or that's why what Aurora Limitless is doing, where the application doesn't really need to connect to a specific shard. It just mentions the shard key, like the customer ID, and then a coordinator will send the SQL query to the right shard. And this works quite well when you have a single shard transaction. So you have a transaction that touches on only one customer, it goes to a single shard, and then that works. You go through a coordinator, but then you are on a single Postgres node. The problem is when you have cross-shard transactions, just because your queries are a bit more complex, you are looking at the orders, and the orders concern different customers that are on different shards, and you want to see the sum of the amount of orders for the last week, and then you do a cross-shard query. But then, because you have split the database, you don't have the ACID properties at global level. So you lack read consistency, means that maybe it will read a state from a chart that is not exactly the same point in time in the state of another chart. Other limitation with this sharding on top of databases, you cannot have global indexes, you cannot have global unique keys, for example. You cannot have foreign keys from one to the other. So basically, you go into a hierarchical schema where you split on a sharding key, and then everything is not relational between them. It can improve the scalability and the availability, just because if one database is down, not all connections are down, only those who are going to this shard. But the alternative that keeps all SQL features at global level, the alternative is distributed SQL. And there, the idea is to shard, but below the SQL layer. So you provide the SQL processing, parsing the query, building the execution plan. This is stateless, and that can run in all nodes. And then when it goes to read and write the table rows, the index entries, the transaction status or intents, then this is distributed to multiple shards. But because it is below the SQL layer at the logical level, you still have all SQL features at the top of layer. I will show a diagram of it to explain it. But there is also another important thing when we want to distribute Postgres and change the storage, one reason to change completely the storage, reusing the Postgres code only for the query layer and changing the storage. One reason is to distribute it, but there is also another reason. The storage layer has a few weaknesses because Postgres is quite old and was built for very different hardware. And those are quite well summarized by Rick Branson in an article where he mentioned 10 things he hates about Postgres. And he mentions that he likes Postgres, but there are 10 things that's not really easy to work with in production with some operational constraints. And I will not go into all those details. If you run Postgres in production, you probably have seen some of those issues. And they are mostly all related to the storage. A lot are about vacuum, the way Postgres does multi-version concurrency control, and that it has to vacuum. And if it cannot vacuum, then you may have big problems. Another one is about storing in heap tables, and a lot also about high availability storage. One about connection, this monolithic process that manage the connection, not threads, and others about extensions. But basically, there is another good reason to change the storage of Postgres, solving all those issues, and that's also something that Yugabyte does. First, we add a different storage to distribute it, but also to solve those different problems. We don't have heap tables. We store the table in its primary key. We don't have any vacuum problem. We really do garbage collection for MVCC at lower level, SST file compaction, and high availability. This one is easy. Once you have distributed your reads and writes, then you can also replicate them to multiple nodes. And last one, the one that is not in the storage, the threaded connection, we have also changed that in the fork that is YugabyteDB. Basically, the big picture of it, before going to a demo, in Postgres, you have this query layer that processes your SQL and interacts with the local storage through reads and writes. And the idea of YugabyteDB is to run nearly the same Postgres code for the query layer with some adaptations also, of course, because, for example, when you optimize the execution plan, you need to take into account that it is distributed, so the costs are a bit different. But basically, you can connect to any node. It can parse, analyze your SQL query, build an execution plan, execute the execution plan. And what is different is that when it will read or write index entries, tuples, table rows, then it will call the distributed storage through the network. And all those nodes have the two layers, but are really logically separated. And all nodes store a bit of data because of this automatic sharding there. So basically, the idea of YugabyteDB is to use the SQL layer of Postgres for all the SQL features that it provides, and also all the ecosystem that is around Postgres. You have a lot of tools, you have a lot of applications, and plug that on top of storage that is more like Google Spanner architecture, fully distributed, still ACID, but distributed to multiple nodes. That's the idea of YugabyteDB. And I think it's time to show it and demo the main points, elasticity and resilience. So I have started, I've installed it on Kubernetes. I will not go into the detail. All that is documented. I have also a blog post about it. contact me on LinkedIn if you want a link and you cannot find it. Basically, I have a Node.js cluster where I have 4 nodes and the installation installed stateful sets. So in 3 availability zone, 1A, 1B, 1C, because that's the goal. I want to be resilient if one zone is down or inaccessible. And I have deployed a stateful set for the YBT server, which is really what corresponds to this schema, what we will scale. And there is also a YB master that is more a control plane that doesn't have to scale to more than 3 replicas, 1 on each availability zone, to be resilient if there is an error. But this holds only the metadata about the cluster. It's not critical in the read and write path, so it doesn't have to scale more than that. The tablet server, this is where data will be stored, and this is where you will connect to, and those can scale out. For the moment, I have 2 replicas of them in each availability zone. So let's look at the pods there. Easy. You see 2 T server in each one, and of course, we have also some services that are exposed. Here are the services. So there are some services with the Postgres endpoint on port 5433, and you have some services with a kind of UI, a web console, and I will connect to it. I have a short one-liner that reads that to give me the URL. I have a QR code, but because this session is recorded, I will stop the cluster before you can watch it. And let's go there and see what we have here. Okay. Here it is. So those are the masters. I have leader and followers. And the tablet servers, those that will hold my data, you can see that I have 2 of them, 0 and 1 in each availability zone, 1A, 1B. For the moment, they have no data and no reads and writes. We will run some load to see what happens. Let's do that directly. So showing the services there, you can see that there is also a load balancer in each availability zone, a load balancer that will redirect the connections to the tablet server in this zone, so 2 for the moment, for port 5433, which is the Postgres endpoint. And I will run pgbench, standard Postgres benchmark. So let me start just a pod with the Postgres image. And I will export the connection info. So this is just going to the load balancer that I've seen before. I started that in zone 1A. So this is in zone 1A. And I run the pgbench initialization that creates all tables. And if I refresh here, I can see that I have some user tablets. Those are how tables and indexes are stored. They are sharded on their primary key or index key, and then stored in tablets in the different nodes. And let's insert some data there. Just running pgbench, inserting with a scale. And if I refresh, so I didn't refresh. I see no write there. If I refresh, I see some writes because this PG bench is inserting data into the tablet. So you can see that I am connected only to one zone, to two tablet servers in one zone, but the reads and writes are distributed across the whole cluster because it is distributed. That's the main point. While it is running, I can show you more details about the tables that have been created. Let's take PGBench account, for example, and you can see that it has multiple tablets. 4, 5, 6. Yeah. So the reads and writes are distributed to those tablets depending on the primary key. And each of those tablets have a leader and followers. The read and write go to the left leader. So for one row, it has one leader, but another row will be in another tablet and go to a leader that is on another node. The idea is that each tablet is a raft group with a leader that synchronizes the reads and writes, and this is how it is consistent. And if the leader fails, we will show that, the follower can elect a new leader. And they can do that because when you write to the leader sends the write to the followers and wait for the acknowledgement of one in this case, because of replication factor 3, the idea is that it waits for the quorum, for the majority, so that if the leader is not there, you know that at least one of the follower has the latest state, and if they all together, they can elect a new leader with the latest state. Here I have some data and I will run some loads. I am still in the Postgres, the container from the Postgres image. I start PSQL and can see, of course, all the Postgres commands run. I can list the table. I can show the details about it. Very similar to Postgres. One difference, we don't store the primary key in B tree, but in LSM tree. I will not go into the detail, but that's more optimized for SSD, for example. We use kind of RocksDB in each tablet for that. And we have also the possibility in an index, you define descending or ascending. We have also the possibility of adding a hash function to it to distribute it directly. If we don't have range queries on it, that's a good solution. Okay. Can look at the size of my table just with the Postgres function, pg table size. And let's run some activity there. Of course, if I go back to the web console and refresh, I can see that here I have some read and write activity that is distributed on all nodes. Again, even if I'm connected only to 2 nodes. Usually the application runs on each availability zones and connects to the nodes that are in this availability zone for latency reason and availability reason. If one zone is down, then the application and the database nodes in this zone are down, but the other just continue. So this is running. You can see the throughput, about 500 transactions per second. And now in another screen, we'll see what is the more interesting features when you want to save cost in the cloud. Here I provisioned only 2 nodes. Sorry, I don't want to cancel that. And yeah, I provisioned only 2 nodes in each availability zone. I will scale that to 4 replicas per availability zone. So let's do that. Look here, if I refresh, so here we had a summary telling me that I have 2 tablet servers in each availability zone. If I refresh, I have 4 now. And you see the new ones, so the old ones were the 0, 1, and now I have 2 and 3 in each availability zone. with not all tablets for the moment. As soon as they are detected, Yugabyte redistributes the tablet peers to be able to balance the load. So you can see that some of those new nodes cannot take writes for the moment, but if I refresh after a while, you will see that they will have some tablets and they will have some leaders. Let's look at a table there and see if I have the new nodes. So I'm in replication factor 3 with 1 leader and 2 followers. But here you see that I have temporarily one more follower in the new node, and this follower even became a leader. And after a while, because I need only 3, it will be removed, but after a while. And this is how it works, completely transparently for the application. The application just continues. You see that the throughput has increased a bit, and the application just continues when you scale up. You may expect that because I doubled the number of servers, you may expect that the throughput doubles. Two things. First, maybe not all tablets are fully rebalanced yet, if I look at the number of tablets. And there is also another thing here. I used pgbench that doesn't have a connection pool. With a connection pool, it would have connected to the new nodes, but I don't have a connection pool. So if I want to balance the connection to the 4 nodes in my zone, I just restart it. It goes through the load balancer and then goes to the 4 nodes there. And here I expect to double the throughput from what I had, so to be near 900 transactions per second. The thing is that with a connection pool, it will reconnect, or if you use the smart drivers, we have forked the Postgres drivers for all languages so that they detect new nodes and can connect to new nodes, then it works like that. And so that was about elasticity. So just checking that all nodes, all zones are taking reads and writes. So everything is rebalanced. And now what happens if I have a failure? So one way to simulate a node failure is to scale down at Kubernetes level to 3 replicas instead of 3. And I will show you on the web console what happened, but look at what happens in the application. So pgbench is showing the throughput every 5 seconds, and you can see that here I have a low throughput for 15 seconds, and then it will go to the normal throughput. What happened here is that I stopped a node. Let me, I will explain more, but let me even simulate an availability zone that is down, 0 replicas in this availability zone. And now I explain what happened. So you will see this drop again there. So the nodes where I'm connected send, read, and write to the tablet leaders. And I add some tablet leaders in the nodes that I stopped there. And the reads and writes are TCP network calls through TCP. And we have a TCP IP timeout of 15 seconds. So no answer from the node that is down for 15 seconds. And then it gets a network error and retry. And within those 15 seconds, that's more than enough for the new leader election on the other nodes. If I check the table there, I will see that I have no leader anymore on 1C. Let me see, 1C servers, only followers, and followers that do not answer because it's down, but we don't care because the other one is answering and we need only one answer. And so during 15 seconds, if there are reads and writes ongoing on the node that is down, it will wait for the TCP IP timeout and then continues, no error at all. Transactions just continue after this. Okay, now two scenarios. Either it is a transient failure and the node is down, and that's the reason why it stays as a follower even if it doesn't answer, because maybe it will come down, and let's simulate that by just restarting those pods. So I have nodes that start again. They have a replica that is just not up to date. And then this replica will ask the leader, what are the latest changes? The leader keeps all changes for 15 minutes. And then if a follower that was down comes back within those 15 minutes, it just quickly catch up and then can even become a leader again. Do we have some leaders in 1C already? Not yet, but very soon there will be some election. If the failure takes longer than 15 minutes, we will not keep the logs forever. We will just consider the node as dead, and a new replica will be started. So we will not have time to show that, but for example, if I go again to 3 replicas, and if we wait 15 minutes, so for the moment, there is a node that do not answer to the heartbeats. This one, quickly it will be flagged as dead. And if it's dead for more than 15 minutes, it will be completely out of the cluster, and the followers that were there will be bootstrapped in other nodes, and everything will be rebalanced again from there. Okay, that's mostly what I wanted to show you, and I think we are nearly on time, so I'm just putting back a slide with my LinkedIn and some links, because Yugabyte is open source. We have some contribution to the community, like the community open hours every 2 Wednesday. We have also a community Slack. Just look at the website or ask me on LinkedIn. And yeah, that's what I wanted to show you. If you have a Postgres application, mostly OLTP, the goal is not to optimize for data warehouse where you may not need all those IC properties. If you have OLTP that needs high availability, you can try Postgres. If it doesn't work well immediately, just open a Git issue, contact on Slack. It's a distributed database. There is maybe some tuning to do, but the goal is that you don't have to change the application code. It will run like Postgres there. This is a recorded session, and I'm there on the chat to answer your question, or on LinkedIn, on Twitter, community Slack, everywhere. And thank you very much.